Hello guys, today we'll discuss about the GATE computer science questions on algorithm subject. So here consider a sequence of 14 elements. There are 14 elements. They're given a sequence of 14 elements. The subsequence sum is S of ij summation of k is equal to I to j a of k. So determine the maximum of this subsequence, the maximum of the subsequence where I is greater than or equal to 0 and j is greater than or equal to I and 14 is greater than j. So divide and conquer approach may be used. So here they are given a 14 elements and subsequence sum expression. So determine the SRIG. So they are given the options. So the correct option is 29 and it is asked in the GATE 2019. So first the understand the subsequence array. Subsequence is an array. Let us consider one example A, B, C, D. So array of this is A, B, A, C, A, D, the subsequence or the first three elements A, B, C, A, B, D, then A, C, D, then B, BC, BD, BCD, and C, CD, and D. So these are the different subsequences in array. So the step one is that they are given a 14 elements of the array. As per the given question, if they want to find the maximum subsequence means here the maximum subsequence. So here the element 6, 3, 13, 4, 4, 12. So these are the maximum subsequence. So it gives the result of like addition, it gives 42. But according to the given recurrence relation, the S of ij, the recurrence relation that they are given, the subsequence should be continuous. Here the subsequence, it should be continuous. So the subsequence should be continuous, and here the instead of the 6, 3, 13, 4, 4, and 12, this is not a continuous subsequence. So for continuous subsequence we consider like here from 6, 3, minus 1, minus 2, 13, 4, minus 9, minus 1, 4, and 12. Here up to this we can consider for subsequence continuous sequence. So 6, 3, 9, 9 minus 1, 8, 8 minus 2, 6, 6, 4, 10, 10, 23, 23 minus 10, that is 13, 13, 4, 17, 17, 19, 29. So the answer is 29. So we can get the maximum 29 maximum sequence of sum. So the answer is 29. So the next question is, an array of 25 distinct elements is to be sorted using the quick sort. 25 distinct elements, they are sorted in a quick sort. Assume that the pivot element is chosen uniformly at random. Pivot element that is chosen uniformly at a random pivot element in a sorted in a quick sort. So the probability that the pivot element gets placed in the worst the probability that the pivot element gets placed in the worst possible location, in the first round of the partitioning. So the rounded off to 2 decimals. So here the for quick sort that determines something called as a pivot, and which is a somewhat arbitrary element in the collection, the pivot element. So given there are 25 distinct elements elements are sorted using the quick sort. How many? 25. So pivot element means it's uniformly random. The pivot element is a uniformly random element. So the worst case position in the pivot element is either at the first or last in the quick sort. If we consider this worst case position, the worst case position in the pivot element is either the first or last. So there are two possibilities. So there are two possibilities out of the 25 distinct elements. So how much we got? 0.08, 0.08. So that is the first option. Consider the following statements. Consider the following statement, that is, the smallest element in a max heap is always at the leaf node. The smallest element. They are asking which statement is true. The smallest element in the max heap is always at the leaf node, the max element. The second largest, the smallest element in the max heap means the element, the key element will be, is the, it is a larger, the large element, and whatever the in the heap we will get the leaf, okay, it will be a smallest element, the smallest element in the heap. Okay, maximum heap means this particular key will be the large element. So the second largest element in the max heap is always a child of the root node. The second largest element, suppose here in this case the second largest element in a max heap is always the child of the root node. A max heap can be constructed from the binary search time in O of n time. Maximum max heap can be constructed from the binary search tree in O of n time. A binary search tree can be constructed from a max heap. So this is wrong. So first three are correct. A max heap can be constructed from a binary search tree in O of n time. So option 1, 2, 3 are correct. So heap is a special tree based data structure in which the tree is completely binary tree. The tree is a completely binary tree, and generally the heaps can be of two types, max heap and min heap. So the max heap, the key in max heap, the key that present in the root node, that must be the greatest among the keys present at all of its children. So the max key means the root node, the max key that present at the root node, it must be the maximum. It must be maximum or greatest among the keys present, okay, of its children. So the same property must recursively true for all the subtrees in the binary tree. Min heap and maximum, there are two types. So min heap means the key element at the root node. So this is the min heap, and this is the max heap. So in min heap, the key present at the root node, that must be the minimum among the keys that present at all the children's, present at all of its children's. So this is minimum. So this particular, the root node is minimum, so it's a min heap, and this one max heap, it is a maximum one, the greatest element among the its children's. So that is min heap and max heap concepts. Okay, so as the first statement is true, the smallest element in the heap is always in the leaf node, but it depends upon the graph. It may be left or right side of the graph. So here the smallest element, so this is the smallest element in the heap, smallest element in the maximum heap, smallest element in the heap. Okay, so first one is true. Second, the second smallest element in the heap, the second smallest element in the heap is always a child of the root node. Second smallest element. Second smallest element. Second smallest element in the heap is always the child of the root node. Okay. So second is also true, and the third is also converting binary search tree to the max heap that will take O of n time as well as O of n space complexity. Okay, we can't convert the max heap to binary search tree. So max heap can be constructed from the binary search tree. So this max tree that can be max heap that can be constructed from the binary search tree, converting from the binary search tree to max heap. Okay, max heap that can be constructed, that will take the time complexity and the space complexity will be O of n, time and space complexity. Okay. Let us consider one more question. There are n unsorted arrays. Okay, there are n unsorted arrays a1, a2, an. Assume that n is odd. Assume that n is odd. N is a odd, and each of a1, a2, an that contains n distinct elements, and there are no common elements between the. There are no common elements that are between any two arrays. There are no common elements between the any two arrays. So the worst case time complexity of computing the median of the medians of a1, a2, an is. So here the answer is O of n square. Means here there are n distinct elements and there is no common elements between the any two arrays. Any two arrays. So the worst case time complexity of computing the median of this array. The worst case time complexity. The worst case time complexity of this median of arrays. So finding the median in an unsorted array is finding the median in an unsorted array. Unsorted array is O of n, but it is similar to the quick sort, but quick sort that partition will take extra time. So finding the median, that will be like finding the median divided by 2. So if n is odd, the value is ceil I plus j by 2. If n is even, the value is floor I plus j by 2. So here the total number of arrays are total number O of n into O of n. So that is O of n square. O of n square. They are clearly saying that all are distinct elements and there is no common elements between the any two arrays. There is no common element between these two arrays. So O of n into O of n. So O of n square. The correct answer is O of n square. Let G in any graph G be any connected, weighted and undirected graph. So if G has a unique minimum spanning tree, G has a unique minimum spanning tree if no two edges of the graph have the same weight. So if there are no two edges of the graph have the same weight, and G has a unique minimum spanning tree. G graph has a unique minimum spanning tree if for every cut of G there is a unique minimum weight edge crossing the cut. So which of the following statements are true? Okay, so here here both the statements are true. Consider this graph. Consider the given G is connected. The graph is connected, weighted, and undirected graph. A graph is weighted, a graph is connected, and undirected graph. So first point, G is a graph. The graph G is unique and no two edges of the graph is same. Okay, the condition is that there is a unique graph here. There are no two edges of the graph is same. No two edges of the graph is same. So step 1, using the Kruskal's algorithm, arrange each weights. Arrange so each weights in the ascending order. So for this consider this graph, the ascending order is like 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, then 29 and 30. Okay, so each weight is different. Okay, the nodes, two edges in the graph is same. So first is as per the Kruskal algorithm, arrange each the weight in the ascending order. Then after the arranging the in a ascending order, like step 3, here the 17 plus 18 plus 20, 21, 22, 23 and 26. So addition of all these, we are getting the 147. And here all the elements are distinct. So the minimum that is spanning tree is 1. Okay, so here all these, like here there is no cycle is formed here. There is no cycle is formed. So 30, 28. So the first statement that G is a unique minimum spanning tree if no two edges are the same weight. Okay, it is true. And second one is, as per the above graph, if we are cut the edge, that should be the minimum edge because we are already given all the minimum edge weights if the graph is distinct. So 28, 30. So minimum edge, which it is still unique. If we are cut the edge, that should be minimum edge, and all the minimum edge weight in the if the graph is distinct. Okay, for the parameters a and b, so for the parameters a and b, both of which are omega, this is omega of 1. So t of n equal to t of n raised to 1 by a plus 1, and t of b equal to 1. Then t of n is t of n raised to 1 by a plus 1, and t of b if both the parameters a and b. So for this, then what is this t of n they are asked? T of n. So here the t of n is equal to the t of n raised to 1 by a plus 1, and t of b is equal to 1. So here t of n raised to 1 by a square plus 1 by a cube. So t of n raised to 1 by a cube plus 3, 2 plus 1. So t of n raised to 1 by a raised to k, a raised to k equal to k plus b. So here theta of log n. So for any given a and b values in the expression, it is theta of log a log log n to the base b. So n raised to 1 by ak is equal to a, then ak square root of n is equal to a. So n is equal to a raised to k. So k is equal to log into log n. So this is the correct answer for t of n is equal to theta of log a log b into n, log a log b into n. So here let the graph with vertices v and edge e be a directed weighted graph with weight function. This is the weight function they are given. Okay, graph with the weight and edge with weight function for some function f v to r for each edge u comma v. So defines the weight u comma v as u w of uv plus f of u minus f of v. Which of the following option that complete the following sentence so that it is true? So which of the following options that completes the following sentence? The shortest path in the graph g, the shortest path in the graph g under the weight w are the shortest path under the w dash 2. The shortest path in a graph under the weight w, the w are the shortest path under the w dash 2. So the correct answer is for every the function f of f v to r v to r. So here the solution is given. So the w dash p is equal to wp plus the weight h of v naught minus h of vk. So here the path p from v naught to vk, this v naught to vk has this weight w of p plus h of v naught minus h vk, because h of v naught vk they do not depend on the path. If one path from v naught to vk is shorter than another using the weight function, so then it is also shorter using the w dash. Okay, so the option v to r. So next question, let the graph g of v is a weighted undirected graph and t be the minimum spanning tree of g is maintained using the adjacency list. The graph is maintained using the adjacency list. Suppose a new suggested edge. Suppose a new weighted edge v u comma v that belongs to v into v is added to the g. The new weighted edge u comma v, so that is added to the graph. The worst case the time complexity determining if the t is still a minimum spanning tree of the resultant graph. So the correct answer is this one, theta of v. Consider a graph vertex with edge where v is v1 to v2 v100, edges of vi comma vj where I and j are greater than 1, and the less than or equal to 100. So the weight of the edges Vi Vj is I minus j, and the weight of the minimum spanning tree, weight of this minimum spanning tree of the graph G is, so weight of the minimum spanning tree of the graph G is 99. So here if there are n vertices in the graph, if there are n vertices, then for n vertices the number of edges is n minus 1 edges. If there are n vertices in a graph, so for each spanning tree has n minus 1 edges. N minus 1 edges. So if n is 100, if they are given n is 100 vertices, right? So each weight is I minus 1, I minus j for edge vi comma vg, comma vg. So I is greater than or equal to 1 and less than or equal to 100. So here they are given I is greater than or equal to 1 and less than or equal to 100. So the weight of the edge v1 v2 is 1, and the weight of v5 and v6 is 1. Okay, so the weight of the v1 and v2, the weight of v1 and v2 is 1, and the weight of the edge v5 v6 is also 1. So here if I and j, these are all less than 100, so 99 is the edge of the weight, 99. So they are called the weight of the minimum spanning tree of the graph is, so there are 99 edges of the weight is 99. Okay, so here the weight of the edge v1 and v2 is 1, edge of v5 v6 also 1. So if there are 99 edges are there, how many? 99 edges. So for 99 edges the weights will be 99. So consider the following undirected graph. Consider the following undirected graph. So this is the undirected graph. Choose this value for the x. Choose a value for the x that will maximize the number of minimum weight spanning tree. That will maximize the number of minimum weight spanning tree of the graph G. The number of minimum weight spanning tree of the graph G for this value of x is, okay, choose the value of x that will maximize the number of minimum weight spanning tree of the graph. So the number of minimum weight spanning tree of the graph for this value of x is, so here the answer is 4. The number of minimum weight spanning tree of the graph G for this value of x, for this particular value of x is 4. This value of x is 4. So here if x is 5, because it is having the maximum number of spanning tree. If suppose x is 5, because it's having maximum number of spanning tree, okay. So if x is 5, then the total number of minimum weight spanning tree are 4. If x is 5, if the x is 5, then minimum weight spanning tree are 4. So here the x is 5, then the total number of minimum weight spanning tree are 4. X is 5, here the x value is 5, because it is having the maximum number of spanning trees. If r is equal to 1, if r is equal to 1, so this is the diagram. 4113 4131. If r is equal to 2, if r is equal to 2, the weightage, if r is equal to 3. Okay, so this is the diagram. R is equal to 4, r is equal to 5, r is equal to 5. Okay, so this is the case for if x is x is equal to 5, it is having the maximum number of spanning tree. So the total number of minimum weight spanning tree, the number of minimum weight spanning tree of the graph G for the value x is, for the given value of x is, this value of x is 5. This, so here we will get 4, the x value is 4, x is 4. If x is equal to 5, then the total number of minimum, the number of the minimum weight spanning tree is 4. Consider the weights and the values of the items listed below. These are the weights, they are given weight and their value of the items are listed below. Note that there is only one unit of each item. Consider there is a weight and the values are listed below. So note that there is only one unit, of each item, only one unit of each item. So here the task is to pick a subset of the subset of these items such that their total weight, so their total weight is no more than the 11 kgs. Okay, so here the weight they are given 10, 7, 4, 2, and note that there is only one unit of each item, only one unit of each item, and the task is to pick the subset of these items such that the total weights is not more than the 11 kgs and their total values are maximized. So moreover, no item may be split. So the total values of the items picked by an optimal algorithm is denoted by the V opt. So a greedy algorithm that sorts the items by the value of the weight, a greedy algorithm that sorts the items, by their value to weight ratio, in the descending order, and packs them greedily. So starting from the first item in the order list. So the total value of the items picked by the greedy algorithm is denoted by the V greedy. So the value of the V opt minus V greedy is 16. So we'll see the solution. So here the weight, and the value, here the value, the first sort the value weight in a descending order, the value weight in a descending order. So the value weight in a descending order. So here the ratio, the value weight in a descending order. So here we'll get like the value by weight, the value by weight. So here the value by weight in descending order. So value is in 24 by 2, that is 12. 24 by 2, 60 by 10, that is 6, 20 by 4, 5, 28 by 7. So 7 4s are 27. So this is the in descending order for this question. So V opt is clearly the 60. So V opt is clearly 60. For V greedy, use the table that do not take the fraction as per the question. So item 4 that picked and a profit of 24. So this particular item 4 is picked, the profit of this value profit 24, and the remaining weight remaining weight is, so this 11 minus 2, 11, the remaining weight is 11 minus 2, so that is 9. And next item 3 is picked. The item 1 cannot be picked since its capacity is greater than the available capacity. The capacity is greater than the available capacity. So in the item 3, so it's a 24. So 24 plus 20. 24, the item 3, so 24 plus 20. So here in case 24 plus 20, that is 44, and remaining capacity is 9 minus 4. So in first case, the item picked is, the profit is 24, and the remaining weight, so here when the item this 24 is picked, so value, the weight is 12, so the remaining weight is 11 minus 2, this one 11 minus 2, 9. So when the value 24 is picked, 11 minus 2 is 9. So now the value 3 is picked. So in the case of value 3, this item 3 is picked, and the profit is like 24 plus 20. So 24 plus 44, and the remaining weight is this 9 minus 4. 7 plus 2, 9 minus 4 is 5. Okay, 9 minus 4 is 5. So now no item can be picked with the available capacity. So greedy is 44, means 60, the 60 minus 44, that is 60 minus 44, so that is 16. So here the task is to pick the subset of these items such that their total weight is not more than the weight is not more than 11 kgs, and their total value is maximized. The total value is maximized. Moreover, no item may be split, and the total value of the item picked by an optimal algorithm is denoted by the V optimal. A greedy algorithm sorts the items by their value by weight. This ratio, value to weight ratio in a descending order, and packs them greedily. So starting from the first item in the order list, the total value of the item picked by the greedy algorithm is denoted by greedy. So the optimal minus greedy. So here the value weight is decreased item. So this the decreased value, the value by weight, and optimal V optimal is clearly 60. The V optimal is clearly the 60, and greedy use the table, do not take any fraction per as per the question. So when the item 4 is picked, the profit is 24, and the remaining weight, the remaining weight is, so when this particular item is picked, so in this remaining item is picked, so this 11 7 plus 11 minus 2, so that is 9. So next item 3 is picked. 1 cannot picked because its capacity is greater than the available capacity. Okay, so its capacity is more when this particular item is picked. So profit is 24 when item this is picked. Okay, so 20, right? And for this item 24, so 24 plus 20, 44. The remaining capacity is 9 minus 4. So for greedy, for optimal minus greedy is 16. Okay. Next, consider the following function from the positive integer to real numbers. Consider the following function from the positive integer to the real number. So the correct arrangement of the above function, this is the function they are given above. The correct arrangement of the above function in the increasing order of asymptotic complexity. So the correct option is 100 by n. 10 means we have to arrange from positive integer to the real numbers, so 100 by n, then 10, then log n to the base 2, then square root of n and n, So in this problem they are expecting to find us increasing order of asymptotic complexity, increasing order. So in the step 1, take suppose if the value of n is 2048, the value of n is taken as 2048, that is 2 raised to 11, right? 2 raised to 11. N is a very big number. Okay, always take the n is very big number. Step 2, divide the function into two ways, one polynomial function and exponential function. Step 3, the above functions are belong to polynomial, so simply substitute the value of n. So first compare with the constant value. So here the first is 100 by n. So 100 by n means 100 divided by here 2048. So we'll get the 0.0488. Then second is 10. 10 is greater than, okay, increasing order, no? So here 10 is greater than this particular number, right? Then log n to the base 2. So log n to the base 2. Okay, so here we will get log n means 2048. So log n, so log 2 raised to 48 means what? 2 raised to 11 to the base 2. So this is 11, right? So the first, this is third, and next is square root of n. So square root of n will get 45 point, then n value 2. So here they are asked about increasing order of the asymptotic complexity. So Here the order will come like 0.048, then comes the 10, then comes the 11, then comes 45.2, 45.25, then 2048. So this is the order that we are getting in the increased order, right? Next question. So consider the following table. Consider the following table. The algorithms they are given and the design paradigms. The algorithms and the design paradigms, right? So algorithms like Kruskal algorithm, quicksort algorithm, and fluid Warshall algorithm. So if you know at least two, then you can match up the following these algorithm to the design paradigms. So here, as you know, quicksort is a divide and conquer algorithm. Divide and conquer algorithm. Which one? This quicksort. Quicksort is a divide and conquer algorithm, and fluid Warshall is a dynamic programming algorithm. So Kruskal is a greedy algorithm. Kruskal algorithm is a greedy algorithm. So the option is 2, 1, and 3. 2 means Kruskal is a greedy algorithm. Quicksort is divide and conquer algorithm. Then fluid Warshall is a dynamic algorithm. Kruskal and Prim's algorithm. These are greedy algorithms finding the minimum spanning tree. So these are by okay. So the Kruskal and Prim's algorithm. Kruskal and Prim's algorithms are for finding the minimum spanning tree. Or for minimum spanning tree. So to find this minimum spanning tree, we are using the greedy techniques. We are using the greedy technique for the minimum. So the Kruskal algorithm and Prim's algorithm, these are finding the minimum spanning tree. So to find the minimum spanning tree, we are using the greedy techniques. And quicksort algorithm is a divide and conquer algorithm. Fluid Marshall algorithm is for solving the all pairs of shortest path problem using the dynamic programming. Fluid Warshall algorithm. It is used to solve all the pairs of the shortest path using the dynamic programming. All the pairs of shortest paths. Okay, Kruskal and Prim's algorithms are used to find the minimum spanning tree using the greedy technique. And a quicksort is a divide and conquer algorithm, and a fluid Warshall algorithm is for solving all the pairs of shortest path, all pairs of shortest path problem from the dynamic programming, all pairs of shortest path problem using the dynamic programming. Okay, so there are some important points regarding this greedy and dynamic programming. Greedy, Kruskal, and the greedy techniques. Kruskal and the Prim's algorithms they used for finding the minimum spanning tree. So here the greedy it is always gives a polynomial time complexity. The greedy algorithm it always gives a polynomial time complexity. It is not an optimal. It is not an optimal, and it always selects only either the minimum or the maximum among all the possibilities. So greedy algorithm that selects a minimum or the maximum among all the possibilities. So it is not an optimal. Dijkstra algorithm for shortest path finding, optimal merge patterns, Huffman coding, so fractional knapsack algorithm, okay, knapsack problem. So these are all that use the particular this greedy algorithm. And for dynamic programming, it gives either the polynomial or the exponential time complexity. It gives always the optimal result. And it checks all the possibilities of the problem. So the longest common sequence for matrix chain multiplication, traveling says problem, so that all comes in the dynamic programming. So longest common sequence, matrix chain multiplication and traveling cells problems. So that comes in the dynamic programming. Let us consider one more question. Let the graph v comma e vertex edge is connected to any undirected edge weighted graph. The weights of the edges in E are the positive and distinct. The weights of the edges in the E are the positive and the distinct. So consider the following statement. So minimum spanning tree of the graph is always the unique. Okay, it is true that we already discussed this. Minimum spanning tree of the graph is always a unique, and the shortest path between any two vertices in the graph is always unique. So only the first statement is true. If the graph that is having all the positive and the distinct unique values, no duplicates, then the statement 1 is definitely it is correct, because if we are using the either Prim's or Kruskal algorithm, it gives a unique spanning tree. If we use the Prim's algorithm and Kruskal algorithm, so we'll get a Kruskal algorithm will get a unique minimum spanning tree. Okay. So the next question. So this is the explanation. So using the Kruskal algorithm, the arrange the each weights. We already discussed the same problem. So use the Kruskal algorithm to arrange the each weights in the ascending order. So for this 17, 18, 20. So in using the Kruskal, all the weights are arranged in the ascending order. And in the step 2, so here uh, with this addition, with this particular this cyclic, it is removed in the Kruskal. So unique weight, so the addition is 147. Here all the elements are distinct. So here the minimum spanning tree algorithm is 1. So Kruskal minimum spanning tree algorithm. So given a connected and undirected graph, a spanning tree of that graph is always a subgraph. So this it is always a subgraph of the spanning tree, that is tree, and connects all the vertices together. So a single graph can have the many different spanning trees. Single graph is having many spanning trees. So a minimum spanning tree or minimum weight spanning tree for weighted, connected and undirected graph is a spanning tree with the weight less than or equal to the weight of every other spanning tree. The weight is here, this some of the edges are removed, so it is very less than the other spanning tree, and the weight of the spanning tree is the sum of the weights given to the each edge of the spanning tree. So how many edges does the minimum spanning tree has? How many edges does the minimum spanning tree has? So a minimum spanning tree has v minus 1 edges, where v is the number of vertex in a given graph. Okay, so with respect to that, so may or may not, in the second start statement, that example of the graph, okay, it is not correct, it is not an appropriate answer. So let us discuss one more question. Let A be an array of the 31 numbers that consisting of sequence of zeros followed by the sequence of ones. The problem is to find the smallest index of I such that A of I is 1 by probing the minimum number of locations in the A. So the worst case number of probes that are performed by the optimal algorithm is, so there are 31 numbers, the array of 31 numbers. So if you apply the binary search to find the first occurrence of ones in the list, it will give us a smallest index I, where the one is stored. So here, as in this array of sequence, zeros are followed by the sequence of ones in a sorted, we can apply the binary search directly without the sorting it. So the number of probes is, so C log 31 to the base 2, so that is 4.95. So here we are using the ceiling, so it becomes the 5. Okay, so here the 4.95 we will get log 31. There are 31 elements, are 31 to the base 2. So here we will get the 4.95. Okay.